Okay, good afternoon. Welcome back after the informal 1 week break, right? We did not see each other in the last week. I upload a video file, sort of e-learning, so it covers the first 2 sessions of chapter 2, which I presume, all right, most of you, I cannot presume everyone, but most of you should have watched, all right, the video. All right, so I will quickly run through those 2 sessions again, and then we're supposed to continue and start with session 3, continuous distribution. But before that, there is an announcement on the midterm test. I've been telling you that, okay, it's Saturday, but unfortunately it seems that a lot of problems that the test held on Saturday. So we finally make it to Tuesday, week 8, I think it's 12th of March, in the evening, or in the night, if you can call it, 8 o'clock to 9 o'clock, evening. Don't come and tell me that you have clashed with your class schedule. We believe that there shouldn't be any class, all right? So we have already, I already uploaded an announcement an hour ago, so you can check it, all right? Here's the announcement. So it's on Tuesday, 12th of March, from 8 o'clock to 9 o'clock. Oh, wrong button. Okay, so it's the 12th of March, Tuesday, 8 to 9, multi-purpose sports hall, hall 2. All right, I think it's upstairs if I'm not wrong. All right, a multi-purpose sports hall for exchange student use. It is somewhere near the sports complex. All right, you can find it on the map. Scope of the test. It covers the first 2 chapters, chapter 1 and 2. All right. It's closed book exam, a closed book test, but you are allowed to bring in 1 piece of paper. Okay. You have an option not to bring any. You can have option right on one side, or you can use both sides. All right. But I would say that try to use maybe one side. The reason is that maybe in the final exam, you still just have 1 piece of paper. If you fully utilize all the spaces, then what happened to the chapters 3, 4, 5, 6, 7, and so on? Okay, the idea is that it's not copy everything, every line of the lecture notes or tutorial solutions into the help sheet. You have to do the revisions. You have to know what is important, and this help sheet just helps you release from the chores of memory, the formulas. All right. So 1 piece of help sheet, A4 size. You can bring in calculators and make-up test. Those with valid reason, like these are some examples. Or if you fell sick, fall sick on the date, then with MC, then you can participate in take part in the make-up test. All right. You have to play. I don't know whether you have driving test in the evening. So driving test is not a valid reason for make-up test. All right. Okay, you read it yourself. So just let you know that the test time and date had been finalized. Is on the 12th of March, Tuesday evening, from 8 to 9 o'clock. Covers chapters 1 and 2. All right. Okay. Okay, so just briefly run through the sections 1 and 2. So basically, chapter 1 is on random variable. So what is a random variable, and how is it linked to what we learned or what we discussed in chapter 1? So basically, a random variable is a variable, so it consists of values, and associated with values there are number or something that associate how likely you will see such values of the random variable. But the definition of random variable basically is a function. A function. So a function is to map Okay, so basically it's a function. A function is to map the sample space to a real number, a set of real numbers. All right. So so I give you an example to give you an idea again what random variable means. So I consider an experiment of tossing 3 coins. So a sample space is considered of the outcome of this tossing 3 coins. So this is the sample space, consists of 8 equally likely outcomes. All right. So you can consider you label the 3 coins with different colors or different labels, 1, 2, 3. So the order has meaning. All right. Then we try to map. So for this sample points, we map to a number 3. So basically, it means that this mapping is trying to find out how many heads out of these 3 coins. So 3 heads, so x equal to 3. If you got 2 heads, then x equal to 2. So this is to take up, for example, if you see h, then it will map to the point 3. All right. So so altogether there are 8 sample points. So you map to some numbers in the real line, and in this case, it's 0, 1, 2, 3, and it represents the number of heads. All right. So the range of the space, that means the possible values for your range is, in this case, is 0, 1, 2, and 3. All right. So although I set map to a set of real numbers, so basically in this example, there are only 4 values. Equivalent events. This is try to link up this random variable with something, the outcome of an statistical experiment or the sample space. How to link up an event in the sample space and your random variables. So here is an example. All right. So I look at this part, I take a subset B, all right, and A is a subset of S. Then we say that the 2 events are equivalent, all right, if the probability are the same. All right, so here's a simple example. If I say, all right, x equal to 2, x equal to 2, all right, x equal to 2, so it's equivalent to 2 heads. So it's equivalent to a set with these 3 sample points. If I say that, all right, x equal to 2 or 3, then it's equivalent to a set with these 4 sample points. All right. So on one hand, we are based on the sample space or the sample points. So define the event as a subset of the sample space. On the other hand, we have this x. So we define a subset of these values of the x. So the 2 are equivalent, the 2 events are equivalent if the probability are the same. Or, okay, I'm sorry, not just the probability, because they are equivalent events. They represent the same thing. It simply presents in a different way. So this, I can call it, I want to have 2 heads out of the 3 coins. So if I look from the sample points of view, it's equivalent to this set of sample points. But if I look from a random variable point of view, it's equivalent to x takes the value 2. All right. So the event, the number, okay, the number of heads equal to 2. So that's the event I'm interested in. So it's equivalent to, if I look at the sample space, equivalent to 4 sample points. Sorry, 3 sample points. HHT, HTH, and THH. All right. But if I look at from the random variable point of view, it's equivalent to a random variable equal to 2, which represent by or equivalent to a set of sample points of HHT, HTH, and THH. All right. So I can also have a set of event represented by this sample points, which is equivalent to x equal to 2 or 3. X equal to 2 or 3. All right. That means it's equivalent to B. B is a subset of the range space. So x equal to 2 or 3. If I translate or describe it, basically saying that I got the number of heads out of these 3 cons is equal to 2 or 3, or a number of heads is greater or equal to 2. Greater or equal to 2. All right? But there is situation where if, for example, I get this event, how to describe this event? An event consists of 2 sample points, HTH and THH. So can I describe it as 2 heads? So it's not complete because this is also 2 heads. This one, H, how about HHT? This sample point is also give you 2 heads. While on the other hand, if you say x equal to 2 is equivalent to this one, so therefore the A here and the B here, these 2 are not equivalent. They're not equivalent. All right. So if you have equivalent events, which basically link up the random variable, the event represented by random variable, and the event represented by the outcomes of the experiment or the sample points should be represent the same thing. So x equal to 2, all right, that's not equivalent to an event like this. Because x equal to 2, you can consider it as 2 heads out of the 3 cons. All right? So they are not the same. So we know what is a random variable. The next thing is to describe the random variable. Describe the random variable. So we call it a distribution. So the idea is that we have the values and also associate to it with a probability or a measure of how likely it is. So in this case, in this example, x takes these 4 values, 0, 1, 2, and 3. So these are the equivalent events. And we learned from last chapter how to get the probability of each of these events. So probability of this event, no heads, is equal to 1x. Probability of 1 head is 3x. Probability of 2 heads is 3x. Probability of 3 heads is 1x. So therefore, x equal to 0 is equivalent to this event with probability 1x. X equal to 1 with probability 3x, and so on. So in other words, if you want to find the probability of the random variable equal to certain values, you may have to go back to look at what is the equivalent event in terms of the sample points. So we can summarize or put this information about the random variable, we call it probability distribution, into a table form for discrete random variable. Later I will tell you what discrete means. All right. But you can display in a table form with 2 rows. One is the values of the random variable, 0, 1, 2, 3. How about 4? Can x equal to 4? Can x equal to 4? What is x? X is the number of heads in tossing 3 cons. 3 cons. So therefore, x cannot be 0. When we say cannot in probability, it means that the chance of such values is 0. The probability is 0. So that's why you don't see 4, 5, 6, 7 or -1, negative. It does not mean anything because we cannot find an equivalent event. When you toss 3 coins, find an equivalent event that will give you x equal to 4 or x equal to 10. How can you toss 3 coins to have 10 heads? No. All right? So that's why you only see 0, 1, 2, 3. And then the second row, I give the corresponding probability, which we just work out. All right? 1x, 3x, and 1x corresponding to 0, 1, 2, 3. So this one is easy because x got only 0, 1, 2, 3, only four possible values. So what happens if x take 100 possible values? So I'm going to construct a table and then with 100 columns to find out all the probabilities, all the probability corresponding to these 100 values. It's still manageable. How about x equal to 1,000? Oh, still manageable. I just spent time to write down all this. How about the possible values of x is the set of integers. Do you know integers? 0, 1, 2, 3, 4. Continue to count until infinity. How can you go into represent it using a table form? Huh? Can we write it in a table form? Yes or no? Yes, I modified it. I don't take infinity. I will stop at some point. And saying that, okay, maybe 0, 1, 2, 3, 4, 5, 6, maybe up to 10. Then the next one is 11 and above. So cover everyone, bigger than 10. That is modify a bit, all right? Or simply give an expression, a mathematical expression or functional form. So that's what we're going to do the second way. So this is a function form to tell you for any given x values, what is the probability that you have, right? This is nothing. This one is basically is the probability of the random variable equal to x. All right, it's given by this formula. All right, we skip this one. How to get this formula is not important at this point. All right, just know that we can express it in a formula. And only when this is important. I saw sometimes some of you may think that this formula, all right, valid for all the possible x values, which is wrong. Because I've already stated that this formula only valid for 4 values. X equal to 0, 1, 2, and 3. How about other values? How about 1.5? I cannot use this formula. So here I say that and 0 otherwise. So long as x does not take these 4 values, 0, 1, 2, 3, all other values, the f of x equal to 0. So in fact, this f of x, this probability of x equal to little x has 2 forms. E equals to this form if x takes 0, 1, 2, 3. And there will be 0 for other x values. So that is another way to represent the probability function. All right? Okay, so we also, in section 2, we talk about discrete probability function. Okay, we have discrete, of course we have continuous. So we have these 2 big groups of probability distribution. One, we call it discrete probability function, or the other one is called continuous. Basic idea are the same, except that we have a different tools or mathematical tools to work on the compute the relevant information about this distribution. All right. So first of all, what is a discrete? So discrete is to make sure that your range space is finite or countable infinite. what? Okay, first of all, finite, everyone knows finite. So the previous example, x takes the value 0, 1, 2, 3. So that is the Rx. Only 4 values. So that is finite. How about infinite? So if x equal to 0, 1, 2, 3, 4, ... Right? It continues to go to infinity. So this one is the x values. The number of x values are infinite. Infinite number of them. But there are two types of infinity. One is countable. Count, huh? You know what is count? Counting, right? 1, 2, 3, 4, 5, 6. That is counting. So long as the infinite, okay, the set of infinite numbers can be mapped to each set of integers, that is considered countable. All right? So to make it easy, usually if they are integers, then even they go to infinity, it's considered as countably infinity. So what is the uncountable infinity? Real line, all right, the whole real line. Even I take a section of the real line, only between 0 and 1. You know how many points between 0 and 1? Infinite number of them. And you cannot map it to integers. All right? Let's say 0 to 1, okay, consider right? And you know how many points between these two numbers? Infinite number of them. You can keep on adding figures to these decimal numbers. All right? So my point is there are situations where you have infinite number of points in your Rx in the range space. So to distinguish between discrete and continuous, basically a very simple one is whether there are gaps between, but that's not the absolute way to do. You just see the range space. That means your possible value of x, whether it can be mapped to whether it's finite or whether if it's infinite, whether it can map to a set of integers, the set of integers. If not, then it's considered as continuous. All right? So basically, a distribution can be represented by these pairs, the x values and the corresponding probability. So that is a collection of all these pairs is considered as a probability function. So in the example here, so basically we have 4 pairs: 0, 1x, 1, 3x, 2, 3x, 3, 1x, which means that x equal to 0 with probability 1x, x equal to 1 with probability 3x, and so on. So there are only 4 possible values. So this is finite. And this is a discrete random variables. So here is the probability distributions. The f of x has the following properties. So it must be greater or equal to 0 for any x values. And second one, okay, why f of xi is bigger or equal to 0? Because xi is part of the, you have an equivalent event for x equal to xi. So here you say that if x equal to xi, there will be an event A in the sample space. So because from chapter 1, we know that probability of any given event is greater or equal to 0. So therefore, this f of xi must be bigger or equal to 0. So just remember, whenever you say this function is a probability distribution, you must make sure that this function is always greater or equal to 0. Evaluate any of the xi values. All right? Second thing, the sum of all this probability has to equal to 1. The sum of all these probabilities, f of xi, has to be equal to 1. So here I say that xi, so basically I take the value from x1, x2 up to x infinity. All right, and sum of all this probability has to be 1. All right, So these are the basic properties. And I also discuss about this interpretation of probability functions. So the usual way to interpret it as follows. X takes this value with this as the probabilities. But I can also interpret in the following way. Here is an example. So I consider the population of NUS student population. All right? Suppose they have 35,000. And X represents the number of modules a student take. So altogether, I have 35,000. Each student suppose have a number. That number represents the number of modules that he or she takes in that semester. So it ranges from 1 to 7. Can I have a 0? It's nothing to do with... can we have X equal to 0? It seems contradicting. If you do not take any modules that semester, you're considered as a leave of absence, right? So it must be at least 1. It's not worth to take 1 module. You still have to pay full fee, right? Except maybe you are about to graduate. All right. Okay. 7. I don't know whether we can have 8. Maybe you need special approval. Anyway, this table tells you one thing. Don't use your sense, what we call your intuition. So here, no 0, because it's given like that. All right, we don't try to over-interpret it. And we don't have 8 or beyond. So this table tells us that anyone from this, make sure. All right. All this add up to 1. If it does not, of all these numbers, does not add up, do not add up to 1, then we have problem. That means there's something that happened with certain probability, but we don't know what that something is, because the table did not tell us, but it should add up to 1. And also every number, every probability given there are bigger than 1. Okay, so the point I want to raise is that this point 0, 1, in terms of probability distribution, it means that X takes the value 1 with probability 0.01. All right? But in this situation, this example, it simply means that there are 1% of the population. Here's another way to look at it. Instead of I'm saying that there are 1% of the population who takes only 1 module. And 3% take 2 modules. 3% of the population. So in other words, for probability function, you can interpret as the probability of the X take that particular values. You can also think of it, you have a population. Here it's very concrete. I have a student population, NUS student population, 35,000. All right? Then the probability function interpret as the proportion of this population have that values. So the most popular one is 39%. 39% takes 5 modules. How many of you take 5 modules? It should be 39, so it means that 4 out of 10 should have this number, if this is correct. But maybe these numbers are cooked up. All right. Okay, so the point is, you treat it as a probability of the random variable take that value, and also you can interpret as a population. And this population can be infinite. All right? And it's the proportion. We can talk about the proportion of an infinite population. For example, toss a coin. The probability of getting a head is equal to half for a fair coin. You can interpret as I toss the coin, all right, from the past to infinity. Infinite number of them. In fact, we don't know how many times that you can toss the coins, right? So it's infinite. So half of these tosses will have a head, and half of it should be a tail. So that's how we interpret in terms of a population. All right? Oh, okay. Too much for the review. I think that's the last slide. Okay. So let's start something new. Okay. Continuous probability distribution. All right? So, Rx, the range space, remember, we say that X is a function to map the sample space to the range space. And this one is an interval or collection of intervals. For any intervals on the real line, there are infinite number of values. All right? So we just specify the intervals. And it can be just a collection of intervals. But most of the time, the intervals that you encountered are like maybe between 0 and infinity, all right? Or from minus infinity to infinity. So these are two common intervals that we encounter, all right? All right, so if your range of the range space is an interval or a collection of intervals of real numbers or real lines, then we say that this random variable is continuous. So then we will represent using a function. The table form is out because you have infinite number of x value. So you cannot represent by a table. It has to be a function, all right, functional form. So f of x, and we call this probability density function. Probability density functions, all right. So again, this function must be positive for all x. Must be greater or equal to 0 for all x in the range space, and the integrate over the range space of f of x dx equal to 1. What does that mean? It simply means that the probability, all right, over all these possible values should sort of add up to 1, all right? And okay, so, or we extend it to integrate from minus infinity to infinity f of x dx equal to 1. Okay, this is for convenience. We write it like that. What's the difference between these two? Suppose, let's say, Rx equal to 0 to 1. 0 to 1. So our f of x, the density function, only defined over this range, this interval from 0 to 1. Beyond that, from minus infinity to 0 and from 1 to infinity, all right, then we just take the f of x, the density function, as 0. So we will define f of x equal to 0 for any x between minus infinity to 0 and or x is between 1 and infinity. Then f of x equal to something which is non-zero, where x is between 0 and 1. All right? So you just have to understand that either you just look at your range space, all right? Then you integrate, or that basically sum up all the possible density should equal to 1. But we can make it more general to cover the range from minus infinity to infinity. How can it be the same? Yes, it can be the same from the probability point of view, because from minus infinity up to your 0, in this example it's 0. I put my density function equal to 0. So you integrate it, it's still 0. You see? Put it this way, from minus, now this will be very useful technique, f of x. Suppose my Rx is 0 to 1, all right, for example. So this one, I can write it as integrate from minus infinity to 0, f of x dx, plus 0 to 1, f of x dx, and then plus 1 to infinity, f of x dx. But unfortunately, this f of x are not the same. Huh? This part over this range, I put it 0. So this integration, you integrate something 0. The integrand is 0. That means the integration is 0. Similarly, I put this 0, so this part is also 0. So left behind with this part. This is non-zero. So this part is the same as integrate over the range space f of x dx. All right? So I just want to show you that these two are equivalent. You integrate over the range space of the f of x. It's the same as integrate from minus infinity to infinity f of x. But these two are not exactly the same. F of x over the Rx, yes, okay, but then beyond the Rx is defined as 0 in order to make it work. All right, so this is what I said. So for those x not in Rx, I define the f of x as 0. So then the left-hand side and the right-hand side are the same. All right? Okay. So this is particular about the continuous distribution. So we talk about the random variable takes the values between C and D is equivalent to integrate the density functions, all right? Integrate the density functions from C to D. Here is the picture. All right. So this is the density function. All right. So probability of x between C and D is to integrate from C to D of this. So it's this portion represent the probability. All right. So let me explain the term density. What does it mean? So I just repeat this again. So I enlarge it so that it will be something like this. All right. There will be this part, right? So I look at this x and x plus delta x. Delta x can be very small. So x plus x delta x. So I'm talking about the range from x to x plus delta x. So what is the probability of x between the random variable x between x and x plus delta x? According to this definition, it's integrate from x to x plus delta x f of x dx. All right? So basically this area represents the probability of the random variable x falls between little x and little x plus delta x. All right? So that's the probability. So now if this width is very, very small, then this area, basically this probability can be represented by probability or f of x times delta x. Am I right? This height is f of x. The height, each point on this curve represented by f of x. So this point is f of x. This is x, this is f of x. All right? So if it's very small, then this can be considered as flat. So it is the height times the width. The height times the width. F of x times delta x. Right? So here is the magic part. So the probability lies between x and x plus delta x is almost equal. If delta x is very small, it's almost equal to f of x times delta x. Delta x is the width, if the width is very small. So if I move this to the other side, so this one is f of x. This is the probability. You divide by the width, so that becomes the density. The density, right? In physics, right? What is density? Mass over volume is I mean, one kind of the definition of density. So it's now I'm the probability divided by the width. So that will tell me the density. So if the density is big, so that means within this small interval, I have a big density. Okay, sorry, big probability lies within this interval. If the density is small, that means within this small interval, the probability fall in this is small. So the density represents how likely that it falls between x and x plus delta x. All right. Now, because it's continuous, it doesn't matter whether it is greater or equal or just less, x between c and d. So these two limits can be replaced by inequality instead of including the equal sign. So in other words, all these four, all these four probabilities, all right, they are supposed to be different events, but it doesn't matter for continuous. Why? Because for continuous random variables. So follow from the definition. So x between x naught and x naught. The probability of this one is equal to x naught, f of x dx. And from calculus, you know that if the upper limit and the lower limits are the same, this integration will give you 0. So in other words, for continuous, I have to stress continuous random variables, the probability of x equal to a particular value is very small. Small in such a way that it's equal to 0. You cannot get the probability. Okay. For example, our height is supposed to be continuous. An individual, if I select an individual and measure his or her height, it's supposed to be a continuous random variable. All right? But because of our measurement instruments, we cannot measure the exact values. How tall are you? For example, how tall am I? Maybe 1.75, right? But in fact, my height is not exactly 1.75. It may be 1.75, maybe 1, 2, 3, 4, 5. I mean, there's a bunch of things, all right? So you have to make sure that you understand the idea. Continuous random variable is very hard to hit that particular value. That's why the probability of the random variable takes that value is 0. But you can have, okay, my height. What's the chance that, okay, maybe I select 1. What's the chance that this guy's height is between 1.75 and 1.755? An interval, all right, between 1.75 and maybe 1.75 and 1.76. So I can get, okay, try to express this probability. But the probability of x equal to 1.75 is 0 if you think that the height is a continuous random variable. All right? So just remember, x equal to 0, the probability is 0 because of that. So all these four probabilities are the same. It doesn't matter whether you include equality or not. I have to stress only for continuous random variable. For discrete random variable, you cannot. They are not the same. All these four are different, maybe. Okay. So, this is another very, very important concept in probability. We know that probability of an empty set is 0. This is true. All right? But it does not mean that if you have a probability of an event A equal to 0, does not mean that A is empty set. For example, if I go back to the example of tossing 3 coins, all right? So the probability of getting 4 heads in the example of tossing 3 coins, this probability is equal to 0. But the event itself, all right, the event itself is there, but it's just no way that you can get 4 heads. All right, the event is get 4 heads. The event is, the event, you must distinguish an event and an impossible event. Impossible event is the probability equal to 0. But the event is not empty set. I'm not saying that you cannot have x equal to 4. You can have x equal to 4, but the event can have x equal to 4, but the probability of this event occur is impossible. So you have to distinguish. These two are not equivalent. All right? When this is equal to 0, does not mean that A equal to 0, empty set. Does not mean A equal to empty set. You can have a set such that it's not empty, but the chance of this set or this event to occur is 0. So from practical point of view, that means it's impossible that you will see this event to occur, but does not mean that the event is, or the set is an empty set. Okay, so if x assumes values only in some interval a, b, we may set f of x equal to 0 for all x value outside a, b. All right, so the same for the discrete random variable. You can set all the values outside your Rx as with probability equal to 0. Okay, let's look at some examples. So suppose x is continuous and the PDF, the probability density function, is given by this. All right, so this is continuous. Why? Because the Rx is an interval between 0 and 1. Between 0 and 1. So long as x between 0 and 1, the f of x is given by Cx. So in other words, the graph will be like this. 1. This is the x value. So it's like that. All right, and 0 here and 0 here. All right. Cx is a straight line. Can I have this one? Zero here, and then come up down, and then. Can I have that? For this f of x, the density function? Yes? No? I don't know. Huh? This slope. Is it positive slope or negative slope? Huh? Don't know. Is it increasing? When x increase, is this line increase, the f increase, right? So the slope is positive. That means it should be positive slope. When you differentiate, it should be positive number. The other one, what's the slope? Decreasing, right? So differentiate negative. So can I have that? Huh? Okay. You find out yourself. All right? But I just want to emphasize. Here, I did not give you the C, so you have to figure out what the C is. How do I know that? Can C be any number? No. C has to be a value to make sure that f of x is greater or equal to 0. All right? C cannot be negative. All right? Secondly, there's another condition. The area under the PDF, so I integrate from minus infinity up to positive infinity, so that means the area under this curve has to be 1. This part is 0, this part is 0, no area. Only this part is area. So make sure that this area is equal to 1 to identify your C. Okay, so here are the questions. Find the value of C. Why we need to find the value of C? Because we need to know the full picture. Otherwise, C can be any number, but C cannot be any number. It has to be a number so that it satisfies f of x greater or equal to 0, the first thing. The second thing is that integrate from minus infinity to infinity, the PDF has to be 1. All right? And after that, complete. We know what, once we calculate C, we know everything about this random variable in terms of the PDF. Once you know the PDF, you know everything. You can calculate the probabilities of whatever you want. You can also calculate other things about this random variable, such as expectation or variance, things like that. Okay, so here we first calculate what is C. So we do the integration. Suppose, okay, this one I use this Rx f of x dx. Alternatively, you can integrate from minus infinity to 0. All right, 0 dx plus integrate from 0 to 1 cx dx plus integrate from 1 to infinity 0 dx. All right, they're the same now. All right, so oh, by the way, I presume that everyone knows how to do the integration. Okay, so I won't discuss it, so you have to check, revise, review how to do your integration for one variable case. All right, so it turns out that this equal to C over 2, and we make sure that this equal to this integration equal to 1. So in other words, this must equal to 1. So by doing so, our C has to be 2. You cannot have other values. C has to be 2. C has to be 2. All right? Okay, I realized just now when I talk about this one, this graph is wrong. All right, this is not Cx. This graph is not Cx. All right, Cx, when C is negative, it should be below. It should be something like this, which is not what we want. This one, this line has a different formula, not Cx. All right, this is not y equals Cx. This is a different formula. So a little bit about confusion about this. So we stick to this one. If I have negative slope, Cx is like that. All right, this is not Cx. This is something minus Cx. All right. Okay, so we work out C. So now I base on C, all right, equal to 2, and then I work out all the probability. So probability of x less or equal to half. Now, you see, this one, what does that mean? It means that x between, what's the lower bound of the x? It's supposed to be minus infinity up to half. All right, so if I go back to the graph, 0, 1, so now we know that this slope is 2, 2x, y equal to 2x, or f of x equal to 2x. All right, so x less than half is supposed to be this probability. But strictly speaking, it is from minus infinity up to this point. That's what x less than half, less or equal to half means. X can be any number less than half. So minus 1 also satisfies this. All right, minus 1. So it's from minus infinity up to half. But this probability, suppose from minus infinity up to half, f of x dx. But I have to stress this f of x takes different form over different range of x. This f of x equal to 0 when x is from minus infinity up to 0. It is 0. But then from 0 onward up to half, the f of x equal to 2x. All right? So in this case, we have to integrate from minus infinity to 0, 0 dx, plus integrate from 0 to half, 2x dx. All right? So I didn't write down the integral from -infinity to 0. So I presume that you are aware of that. All right? But if you want to do it systematically, x less or equal to half means from -infinity up to half. But because of this range have a different form of f of x over different range of x values. So you have to take that into consideration. Okay, so the answer is 1/4. All right? Then the second part, you just, this one is obvious. Because now you don't have the lower bound being -infinity. You start from 1/3 to 2/3. So you just integrate from 1/3 to 2/3, and the answer is 1/3. Okay. So this one also, we don't have the upper bound. Okay, the lower bound is 3/4. So this basically is saying that x has to be greater than 3/4 and up to infinity. All right, but it's equal to 3/4 to infinity f of x dx, and f of x between 3/4 up to 1 is 2x. And then between 1 to infinity, f of x equal to 0. So that's why you don't see these terms. Because it's the integrand is 0, so integrate 0 dx is equal to 0. So we don't have any values add to it. All right? So the answer is 7/16. All right. Okay, here's another example. So we have this time head weight is the time between the two cars pass a certain point. So this time head weight, I fix a point and look at the first car pass this point, all right, and then until the next car pass the same point. So the time between these two cars passing the same point, I call it time head weight. All right, and this one is supposed the behavior of this x, all right, is given by this formula. What does that mean? It means that, okay, this function tells us about the probability density. So if this function is high for a particular x value, that means the time is bigger, all right? The probability of the time equal to that value is bigger, or in the neighborhood of that value is bigger, all right? And this function PDF is equal to that particular form only when x is greater or equal to 0.5. Why not x greater or equal to 0? Is it practical to have x bigger or equal to 0 for that PDF? Obviously it's not. Yeah? Your fixed point here. This is my point. So when the first car passing, just pass this point, then the next car cannot pass the same point at the same time, right? There must be some lapse, time lapse, between the first car past that point and the next car past that point. So here we assume 0.5, 0.5 seconds. I hope it's using seconds. So at least there half a second in between. All right. That's why well, I don't know whether you have experience driving on the road. You can see some car follow very, very close to the previous car. That is very bad. Because they think that they can stop. If the car in front stops, they can stop immediately. But they don't know that when you release your accelerator and press your brake, even your foot is on the brake, when you press it, the car takes time to stop. So you will hit the car in front of you. So my point is that you have to take into consideration there's some time lapse between your reaction and what happened. So the same apply here. I cannot have x equal to bigger than 0 because when the car passed through the first car passed through a certain point, then the next car passed through the same point. It takes time for the next car to pass. You cannot pass at the same time. All right. So x bigger than 0.5. So two things. First of all, is the PDF defined here is always positive. And yes, it is. Because exponential function is always positive. Oh, I have a negative number here. All right. So, any number raised to power a negative number. All right. So long as this number is positive. All right. So, a to power minus b is greater than 0 if a is positive. Because this simply means that it's 1 over a to power b. So if a is positive, no matter how many power you raise or root you take, it's still positive. All right, so this is positive. So e to power minus 0.15 times x minus 0.5 is always positive. And 1.5, the coefficient 0.15 is also bigger than 0. So this one is bigger than 0. The remaining thing is that you're supposed to check whether integrate from minus infinity to infinity f of x dx equal to 1. This is supposed to be integrated from minus infinity up to 0.5, 0 dx, plus integrate from 0.5 up to infinity, this whole thing here. And check whether this is equal to 1. All right? From minus infinity to infinity, integrate to f of x, whether it's equal to 1. So you're supposed to check that. Okay, so we asked. So here I double check. Check how to do integration with exponential function. Exponential function. This one is easier, but sometimes you may need to revise something called integration by parts. Integration by parts. All right. You are assumed to know these things. All right. So for example, this one. All right. So it's equal to integrate 0.5 infinity. All right. Minus 0.15 minus 0.15 okay, because you differentiate it, you have this coefficient, so cancel out. So it's equal to this one. So this one, you can consider integration by parts. So it follows. You will have this. You have this. All right. But anyway, it can be shown that this integration equal to 1. So the PDF given to you is well defined. Next. All right. So we want to know the head wait time is at most 5 seconds. So that is, we want to know at most 5 seconds. At most, so cannot be more than 5. So we want to find the probability of x less or equal to 5. So we just do the integration. So from minus infinity up to 5, but from minus infinity to 0.5, the PDF is 0. While from 0.5 to infinity, but we don't have to work to infinity, we work up to 5, the PDF is given by this. Okay, just a minor thing about the integration. Looks very complicated. But this one basically is 0.15 times e to power minus 0.15x times e to power minus or plus 0.075. All right? This expression, this gives you minus 0.15x. This times this gives you 0.075. All right? It's in the exponent. So therefore, remember EA plus B is the same as EA times EB. All right? exponential also a headache, very complicated function, but it's very beautiful function. So e to power a plus b is equal to e to power a times e to power b. Okay, don't write this as e to power a plus e to power b. This is wrong. Okay, so then I bring this out of the integration. So now the integration needs much simpler. And then you work on that integration. Okay, so the probability is 0.49. So in other words, when you're given a random variable to describe certain behavior, you have to understand the PDF or the probability function. Depends on whether it's continuous or discrete. That distribution, that f of x, tells you everything about the distribution, how it behaves, so that you can calculate the probability of certain events involve these random variables. So in this case, the time headway is at most 5, so it's equivalent to x less or equal to 5. All right. So we just try to use integration to find this probability. Okay. So this f of x, all right, is equal to probability of the random variable equal to x for discrete case. All right, and this one, okay, maybe I should write it. So x between C and D is equal to integrate from C to D f of x dx for continuous. All right. So what I'm trying to say is that this f of x that we just discussed, all right, tells you everything about it, about the behavior of the random variable. For discrete case, it's easy. It just represents the probability of the random variable takes certain values. For continuous case, it represents the density at that point. Or maybe I should write it like this. F of x is equal to probability of x between x and x plus a very small width, all right, and then divide by delta x. All right. This is not in the notes, but then this is what we call density function. The probability between little x and little x plus delta x. So I divide it by the width. That will tell me how likely the x falls between little x and little x plus delta x. There's another way that unify these two definitions. It's called cumulative distribution function. It's defined in this way. I use a capital X. Capital F. Capital F. This capital F, all right, is a function of the little x, and it's equal to the probability of the random variable less or equal to this x values. Less or equal, less or equal. So in this case, I don't have to worry about whether it is discrete or continuous. One definition for both random variables, both types of random variables. But of course, the calculation, the computation will still depends on whether it's discrete or continuous. Okay, so here is a graph to show the idea. So for discrete random variable, my f of x is to sum up all the probability function with a value t, such that t is less or equal to x. Okay, so that's what it means. So I just replace this f of t by the probability of x equal to t. Okay, some of you may have a problem of understanding this. This simply saying that I'm doing a sum. I'm doing a sum. And each term in this sum is f of t. T is the argument or the running index. So you change the t, you have a different terms. So f, maybe f1 if t equal to 1, then f2 if t equal to 2, and so on. So we just add up all those ft such that the t is less or equal to x. All right? So here is an example. For example, okay. For this one, so the probability function, all right, I don't know whether this involved, all right. So the height represents the probability. So the taller, the bigger the probability of the x take that value, all right. So this height represents the probability of x equal to 4, all right. Then how about the cumulative distribution function? So now, this also have one advantage. So I go, the x takes the value until this point. Before I reach 0, I never have any probability. Because for those values less than 0, I don't have any probability. Until I reach 0, then there's a probability. Then f of 0 is defined. This is, you can't see that, it's f0 is very small. Then f1, f2, f3, f4, f5, f6, and so on. All right? So the cumulative, as the word cumulative, it just accumulates. So it just walk along from minus infinity up until you reach x. So on the way to x, whenever you cross any x value that have a probability, you collect it. So you keep collecting until you reach x. So that's how you get your cumulative probability. So you come here. So up to this point, once you collect, it's just like the Pac-Man a long time ago, this electronic game. So once you get that point, you collect the energy, you jump. So here you collect the probability, you jump. How high, how tall you jump? According to what is the probability at that point. The smaller probability, you jump less. The more probability, you jump taller. And this is cumulative, that once you jump, you won't fall back. You keep on going, next point, until you reach the next point, you got probability, then you collect it and jump. Okay? So you see, this is a non-decreasing function. You keep increasing. You can see the horizontal line with two ends are different. One is solid circle. The other one is empty. So it's basically saying that once you reach that, all right, then you continue until before you reach that point. That is still the probability, cumulative probability. But once you reach 4, this one is before 4. Once you reach 4, you jump here because you collect the probability at the point x equal to 4. So you jump. All right? Now, obviously, I have only one formula. Capital F of x equal to probability of x less or equal to x. It doesn't matter what your x value is. It's always defined, always there. For example, what is f of 1.5? Capital F, the cumulative at the point of x equal to 1.5. What is it? So it will be the probability of those probability of, I call it t. T, the value of t is less than 1.5. So in this case, it means that I have to add up, for this example, I have to add up f of, I have to add up f of 0 plus f of 1. All right, just two. Only two values, 0 and 1 has probability. The rest of the x value do not have any probability, so long as it's less than 1.5. All right? How about f of 1.8? So the same. You go from minus infinity up to 1.5. You only cross 2 points that have probabilities, 0 and 1, in this example. So it's the same thing. So that's why it's flat. All right? It's a step function. So this is important. I have to see the link between these two, the probability function, lead to f of x, and the CDF, which is probability function, f of x, and the cumulative distribution function, f of x. How these two are related, and how to get from here to here, or from here to here. All right? So in general, for discrete random variable, the chance of x falls between less or equal to a, greater or equal to a and less or equal to b is equal to probability of x less or equal to b minus probability of x less than a. So you can think of it like this. Okay. For example, this is my A. This is my B. All right. I want to add, oh, I'm sorry, I shouldn't use bar. Maybe I just use lines. All right. Each represent the probability. So if this is A, this is B, for example, all right? Then what is the probability of X between A and B? So I will count this, collect this, add this, and add this. So it's equivalent to probability of X less or equal to B. That means all the probability add up to this point, including B. But I have to subtract those less than A. All right, less than A. But not including A, because A is still part of my probability. So we write it like that. In terms of F, capital F is FB. This one, don't write. This is different from F of A. F of A means probability of X less or equal to A. So this A with a superscript minus, it means that it's a number. This A minus is not A. It's a number slightly less than A. Okay, just slightly less than A. All right. So it's very important for discrete case. It's very important. You have to distinguish between F of A and F of A minus. How about FA plus? Okay, A plus, maybe you can interpret as it's very close to A, but slightly bigger than A. All right, that's A plus. But you seldom see it. Why? Because FA plus and FA, are they the same? Of course they're the same. What I'm saying is that, okay, let's consider 4, for example 4, this point. What is F4 minus? So it's a value less than 4. So it's this value, it's F4 minus. What is F4 plus? It's slightly bigger than 4. So it is somewhere here. So F4 plus is somewhere here. So it's the same as F4. F4. All right, so that's why we seldom mention about A plus, capital FA plus. We only mention about FA minus. Okay. Sometimes some people may just write it like that. A minus. The one that I write given here is A with a superscript minus. So it means the same thing. All right. So yeah, A minus is the largest possible value of X, which is strictly less than A. Okay, in particular, if this A and B are integers, then probability of X between A and B is the same as X equal to A, or A plus 1, or A plus 2, up to B. So this FA minus for integers now becomes F of A minus 1. All right. So in other words, if I'm talking about X between, let's say, 2 and 10, then it's equal to F of 10 minus F of 1. All right. This is the same as 2 minus if your ABs are these are integers, and your possible values. I'm sorry, not AB integer, but the possible values are integers. The possible values are integers. So if A equal to B, then probability X equal to A is equal to F of A minus F of A minus 1. What is this? This is F of A. The lead to F, the probability function evaluate at A. In general, if you don't have this one, then F of A is simply F of A minus F of A minus. All right? That is the jump. So if from F A minus, the CDF up to A minus, jump to f of a. So the difference is your probability value at x equal to a. Remember, all these are continuous for continuous. So this is, sorry, for discrete, discrete. You have this one. If they're integers, then it's equivalent to this one. All right, but for continuous, the story is different. Here is the continuous case. So no more line to represent the probability. The probability is represented by this curve. It's not probability, but the density. The taller the density, the higher the chance that x falls within the neighborhood of x. So the CDF, up to this point, is to integrate the area from minus infinity up to this point. So this area represented by this height. The height given by this height. All right? So you can see that the CDF range from 0 to 1. Range from 0 to 1. It cannot exceed 1 because the CDF represents the cumulative probability. No matter how you accumulate, your cumulative probability cannot exceed 1. All right, so for continuous case, compare with the discrete case. Discrete case is to sum all the ft, t less or equal to x. Here we integrate t from minus infinity up to x. By the way, please distinguish between these two. This is the argument for your integration. So we can use any number you want. But, okay, the lower limit is minus infinity. The upper limit, this value, should be the same as this one. I want to compute f, the cumulative probability up to the point, the random variable equal to x. So I integrate from minus infinity to infinity. Minus infinity up to x. So don't write it like that. I mean, all use x. Because the x here and the x here are referring to two different things. Don't use the same symbol to represent two different things. It will be a bit confusing. So I distinguish it. So for the integration, I use a letter, I use t. You can use any number you. So long any alphabet except don't use x because we are talking about the cumulative distribution capital F evaluate at little x. So don't use that x for your integration. Use some other letter. I use t. All right? So you do the integration on t. After you finish the integration, substitute the upper limit by x. I mean, the upper limit is x. So you substitute the x into your integration minus substitute in the lower limit of your integration. All right? So that's what it means. So how to convert back between f of x and f of x. So from here to here is integrate from minus infinity x f of t dt. From here to here, so you differentiate with respect to x. With respect to x. Then you get back your probability density function. So one is to cumulative, so you do the integration. If you want to get from the cumulative back to the probability density function, you have to differentiate it. It only applies to continuous random variable, not discrete random variable. Discrete random variable, how to get f of x? Don't differentiate, you cannot differentiate it. F of x for discrete case, how to get it? F of x minus f of x minus. All right, the difference between the two cumulative density. One is evaluate x, exactly x. The other one is slightly less than x. So, if the difference is equal to 0 for this case and this case, what does it mean? It means that f of x equal to 0. That means it can never occur at that value. Right? Okay, this one of course provided that the derivative exists. So the probability of x between a and b is just f of b minus f of a. Because for continuous, we don't care about whether it's equal to b or equal to a. It doesn't matter. It does not make any difference. So it's just FB minus F of A. So probability of A less or equal to X less than B, strictly, so strictly speaking, it should be, okay, okay, I'm sorry. This one I already written in this form, and this one definitely is defined in this one. But because these two are equal, so it's the same in this one. Otherwise, it should be F of B minus F of A minus. But it doesn't matter. This and this are the same for continuous. And cumulative at A and the cumulative at a number slightly less than A, the cumulative probability are the same for continuous random variables. All right? So just make sure that you know this basic property is non-increasing because your cumulative probability, once you pass that point, you collect the probability or the density increasing. So, so for any x1 less than x2, f of x1 is less or equal to f of x2. And the cumulative probability has to be ranged from 0 to 1. It cannot exceed 1. Okay, let you think about it. I have this question. For continuous, continuous random variable, can this bigger than 1? Can it bigger than 1? Think about it. Okay, so for continuous case, can this one bigger than 1? The PDF bigger than 1. CDF always between 0 and 1. PDF, the density, can it bigger than 1? All right, so you think about it. Okay, I don't think I have time to start the examples. So I will discuss the examples tomorrow. And I'm going to upload the tutorial 4, right? Next week is 4, right? Yeah. Today or tomorrow. This week? Huh? Every week we have tutorial. That's your job. That's how you get your credit, right? What are your tutorial questions? Okay, midterm test, 12th of March, 8 to 9 in the evening. All right? Cover chapter 1 and 2.